Hey everyone, and welcome to this explainer. Today, we're going on a truly mind-bending journey. We're going to travel from the absolute deepest, most fundamental laws of quantum physics, all the way down to the physical silicon sitting inside the computers we use every single day. It's an incredibly fascinating story about how the sheer, overwhelming complexity of reality literally forces our machines to make some very surprising compromises just to function at all.
To kick things off, let me hit you with a staggering number right out of the gate: 80 to 90%. That is the percentage of all modern AI compute cycles that are actually just hardware-level approximations. Think about that for a second. When those massive language models are doing their heavy lifting, generating text or rendering those crazy images, they aren't actually handing you an exact mathematical truth. At the deepest hardware level, they are fundamentally just guessing.
Okay, let's dive into this. To really ground this idea, consider this quote from the source material by Kyle McLean Smith. He hits the nail on the head, stating that this engine is fundamentally an approximation system, not real arithmetic. The physical chips driving our incredibly advanced AI are essentially bound to make highly educated guesses. They do this because, frankly, it's the only way they can process such massive amounts of continuous data at blistering speeds. But that speed comes with a hidden cost. So how exactly is this guessing game happening physically, deep inside the architecture?
Section 1. The Grand Computational Illusion. Researchers call this process the wood chipper effect, and it perfectly describes how the irreversible loss of data provenance happens step by step. Let's walk through it. Step 1. The AI ingests exact source data, right? Like a copyrighted book or highly sensitive financial records. Step 2. The hardware encounters all this incredibly complex math and approximates it using proprietary, completely secret seed tables that are literally burned right into the silicon by the manufacturer. And finally, Step 3, because that math was just a blurry guess, not a precise, trackable calculation, the original identity and the chain of title of that data are permanently destroyed.
I actually love this smoothie metaphor because it captures the problem perfectly. The hardware basically acts like a giant blender. You know exactly what fruits you tossed into that blender to begin with, but there is absolutely no way you can reverse engineer that smoothie back into the exact individual fruits it came from. Once it's blended, or in this case, approximated by the hardware, that exact digital receipt is just gone forever. But why do our computer chips have to guess in the first place? Why can't they just be exact?
Section 2. The Quantum Observer Paradox.
To answer that, we actually have to shift our focus to the deepest laws of quantum physics. Now stay with me here. In quantum mechanics, there's a well-known interpretation relying on a distinct split between the observer and the system being observed. But what actually is an observer, physically speaking? The academic sources introduce a genuinely fascinating concept called the System Identification Algorithm, or SIA. It proposes that an observer doesn't have to be a conscious human being in a lab coat. It's simply a finite informational agent. Its ability to track and resolve an external physical system is strictly constrained by its own Kolmogorov of complexity. Now, don't let the term scare you. That is essentially just a measure of its memory and descriptive computing resources.
So, the crucial point is this relational boundary right here. A system only appears quantum when its complexity lies below that of the observer. If the observer has enough algorithmic resources and memory to track the system's exact degrees of freedom, it stays quantum and perfectly precise. But once the observer's memory saturates, when the complexity of what it's trying to observe literally exceeds its own capacity, it is forced to irreversibly erase information. The interaction defaults to a classical, lossy reality just to cope with the sheer overwhelming volume of data. This profound theory isn't just abstract blackboard physics either. It connects directly back to the physical hardware bottlenecks sitting inside the computers we use every single day.
Section 3. Hitting the FPU Wall.
And this brilliantly illustrates the whole concept. Dossier #20 states it very simply. The FPU is the observer. Inside your computer, the floating point unit, or FPU, doesn't just passively calculate math. It actually acts as an active, lossy informational agent trying desperately to map an infinitely complex reality into a fixed, finite hardware space.
To really understand this FPU wall, the dossier uses the Pell-Smith sequence as an example of a bit-perfect, absolute mathematical substrate. It's infinite and it's exact. But the FPU, our physical observer, only has a finite register width. So to handle this infinite rational precision, it has to collapse it into rounded, standardized IEEE bins.
Now, this isn't a glitch, it's not a hardware failure, it is simply the natural limit of an observer's complexity. It drops the tiny trailing fractional bits, creating what the dossier calls observer debt. Think about what this means for you and me. Every complex financial model, every medical AI prediction you rely on, is accumulating this invisible debt. It's like trying to fit an infinitely detailed map into a standard-sized envelope. You're literally forced to start folding and cutting corners.
Section 4, Gambler versus the Surveyor. This fundamental limitation brings us to a head-to-head clash between two radically different philosophies of computing, both sitting right inside your machine's physical brain. On one side, we have the FPU Gambler. As we've seen, it's fast, it's lossy, and it relies entirely on those secret proprietary seed tables to make probabilistic guesses. It's basically frantically throwing darts at a dartboard to approximate the heavy math. But on the exact opposite side of the chip, we have the arithmetic logic unit, the ALU Surveyor. The Surveyor is strict, it is totally deterministic, and it acts like a surveyor out in the field using a high-end precision laser. The ALU deals only in 100% exact, verifiable arithmetic. In the world of the ALU, 1 plus 1 equals exactly 2 every single time, absolutely no exceptions. Because it uses absolutely no hidden seed tables or fuzzy rounding bins, it operates the exact same way on literally every single CPU on Earth. It acts as a globally accountable, undeniable universal witness. No matter where you are in the world, its calculation is mathematically perfectly reproducible. So, the big obvious question we face is, if 80 to 90% of our modern AI is currently running on the messy, blurry guessing of the FPU Gambler, how on earth do we fix this hardware flaw?
Section 5, Restoring Absolute Digital Truth. To bypass the sloppy approximations of the FPU entirely, we have to rely on what the sources call a semiotic bridge. This is the universal deterministic interface of structured text. Think of it kind of like a perfect translator. It takes our fuzzy, associative, and highly imaginative human intent, then it safely compiles that intent into rigid, perfectly verifiable hardware execution. And crucially, it maps that intent directly onto the exact ALU.
Let's move to Ergot and see how this builds our actual solution. By intentionally shifting the core mathematical workload away from the guessing FPU and directly over to the exact ALU, we achieve mathematical sovereignty. We completely wipe out that observer debt. Instead of approximations, we restore true reversibility to our computing, which is a nod to Noether's theorem of reversibility. This means we can finally work backward forensically, tracing every single step without ever losing our data's identity to that messy digital blender.
Wow, we've covered a massive journey today, haven't we? Moving from the Komagorov complexity of a quantum observer all the way down to the physical silicon processing logic inside our CPUs. It leaves us with a truly profound realization about the machines we inherently trust to process our world. So I want to leave you with this final, provocative thought to chew on. If we continue building our artificial intelligence and our entire digital future on a foundation of lossy FPU guessing, what ultimately happens to the exact truth of human knowledge? Thanks so much for joining me on this explainer. Keep asking the hard questions, and I'll catch you next time.